So, good morning everyone. So, we have looked at in the last chapter, we have looked at the mechanical properties of solids. In this chapter, we are going to talk about mechanical properties of fluids. And I will just tell you that what we mean by fluids. There are essentially three states of matter, namely the solid, liquid and the gases. And the solids are characterized by having specific shapes and sizes. Okay. And if you apply pressure to it, the change in volume is negligible, and sometimes it is so small that it cannot be recorded. While the same is true for liquids, but the liquids cannot take shear stress at all. So, it does not have any specific shape or size, and it takes the shape of the container that it is put into. And when we come to gases, they have a different property. In fact, the change in volume by application of pressure in gases is enormous, or can be enormous. And like when you fill in automobile tire with air, and by using a device so as to fill in air, the air does not go and settle in the bottom of the tire. Rather, it just fills the space available to it uniformly. While the liquid, actually if you pour in liquid, it will just go to the bottom, run to the bottom and start building up from there. The gases do not have that property. And because the gases and the liquids, they do not have any specific shape, they can flow, and that is why they are called as fluids. So, when we talk about, so we are discussing mechanical properties of fluids, and in that, so far we have defined solids, liquids and gases. It's these two collectively are called as fluids. So, it's the liquid and the gases both can flow, and anything that can flow is called as a fluid. Now, there is another state of matter in addition to the three, which happens at very large temperature, when the atoms are actually stripped of their electrons and they acquire a charge, and these are called as ions. So, atoms either which are devoid of some electrons, essentially which are at the outermost shell, and they form ions, and this state of matter is called as plasma. And some scientists are of the opinion that the colloids, which are the suspension of tiny particles in a liquid such as milk, should also be considered as a separate state of matter. But nevertheless, we shall talk about primarily these three states of matter: solids, liquids and gases. And as I have told that we have mostly dealt with solids in the last chapter. So, we shall be more concerned about liquids and gases or collectively which are known as fluids now. So, we have fluids all around us, and the air that we breathe in is a fluid. Human body consists of water, which is also a fluid, it mostly consists of water, and a lot of processes that go on in human bodies or in other living beings, even in plants, they are mediated by fluids such as water or some other liquid. So, it is very important that we understand the properties of the fluids and the way actually to characterize them. So, let us just go into understanding fluids and also solids from an interatomic or an intermolecular perspective point of view. So, solids, as we know, that have definite shape and size, do not have definite shape and size. And the reason being that the intermolecular force of attraction in solids is very large. So, those attractions or the interactions that keep the molecules stay together, and thus the solids have a definite shape. The intermolecular force of attraction in liquids is small, but not negligible. However, the intermolecular forces or interatomic forces in gases are negligible. So, these are the sort of from the microscopic point of view, we can distinguish the solids, liquids and gases in this particular manner. But what is important for us in this chapter is to understand some of the properties which distinguish them mechanically. That is, some of the mechanical properties which are of relevance to us, such as density and specific gravity. So, if I ask this question whether a block of wood is heavier or a block of iron, you definitely say that a block of iron is heavier, but that is not true. A large log of wood is definitely heavier than a nail or a small block of iron. So, what property distinguishes these two, wood and iron? So, let us talk about density to begin with. So, the word density mean let us denote it by a symbol rho, which is equal to mass divided by the volume. So, m is equal to mass of the substance and V is the volume. So, its density is the property of the substance. So, whether big or small, when a particle or when a particular substance is made of certain material, no matter what shape or size it takes, it will have the same density. So, and the SI unit of density is kg per meter cube. And of course, it also sometimes it's the CGS unit is used of density is gram per centimeter cube, or simply it is written as gram per cc. In general, pressure and temperature will affect the value of the density for a given substance. So, while quoting the density, it is customary to talk about or to mention about the temperature and pressure at which it is calculated. So, I will give you some examples of the densities of certain substances, and you would know that what are the ranges of densities of solids, liquids and gases. So, let us just give you some examples. So, we have solids, liquids and gases, and let us write the material and rho. So, this symbol is called as rho. So, this is in kg per meter cube. Again, we have material and rho in kg per meter cube, and all right. So, we have iron having a density 7.8 into 10 cube. We have an aluminum which has a density of 2.7 into 10 cube kg per meter cube. Wood, usually it is taken as a pine wood. It has a density about 0.5 into 10 cube, and a glass, it is 2.5 into 10 cube. Now, coming to the liquids, it is water, and it is very important to say that at 4 degree centigrade or 277 Kelvin, the value is 1 into 10 cube. And seawater is 1.025 and into 10 to the power 3. Seawater is known to be more dense than ordinary water, and then you have mercury, which is 13.6 into 10 cube, and now we have ethyl alcohol is equal to 0.79 into 10 cube. So, these are for the liquids. As you can see that they are almost one order of magnitude less than the solids, while it is almost of the same density as the wood has in fact a lower density than that of mercury, and even glass has something, glass has density which is lesser than mercury. Now, let us go to the gases. This is air, which as you know is a mixture of nitrogen, oxygen and other gases, and this is 1.29. Remember, there is no 10 to the power 3 here, it is simply 1.29 kg per meter cube. Helium gas is 0.179 kg per meter cube, and carbon dioxide has 1.98 kg per meter cube. So, you see that the gases have a density which are pretty less, very less in fact as compared to the solids and the liquids, 3 orders of magnitude less, and this, as we have discussed, is due to the negligible force of attraction between the atoms or the molecules that constitute these gases. Just to that these all these values that are quoted, they are quoted at a temperature equal to 0 degree centigrade, which is 273 Kelvin, and a pressure of 1 atmosphere. In fact, it is important to as we have talked earlier, that these densities are actually functions of temperature and pressure. So, it is important to mention the temperature and pressure at which they are calculated, or they are the values are quoted. Except for water, the value is equal to 1 into 10 cube kg per meter cube, or 1 gram per cc at 4 degree centigrade. So, let us now do a problem, a simple numerical problem. So, what is the mass of a lead sphere of radius 0.5 meter, given that the rho of lead is equal to 11,300 kg per meter cube. So, in order to calculate the mass, we shall use the formula that mass is equal to density into the volume. So, in order to find the volume, it is a sphere. So, the volume of a sphere is given by 4/3 pi r cube, which is equal to 0.5 cube, which is equal to 0.523 meter cube, and a mass is equal to the density of lead multiplied by this volume, and that is equal to 11,300 kg per meter cube multiplied by 0.523 meter cube. And if you simplify this, it comes out as 5910 kg. So, this is the mass of a lead sphere which has a radius of 0.5 meter. You understand that if we replace lead by an iron sphere or aluminum sphere, this mass is going to be different, because this quantity, even if the radius remains the same, because the density of iron or density of aluminum are different than that of lead. Now, We shall continue with more problems later. Let us now define the other quantity, which is called as the specific gravity. And specific gravity is defined, it is defined as the ratio of a substance divided by the density, a ratio of the density of the substance divided by the density of water at 4 degrees centigrade. So, it is a dimensionless quantity. So, this is density of a substance divided by density of water at 4 degrees centigrade. Now, the advantage of defining this, let us write specific gravity with a SG. This is just the abbreviations used for that, for them. Since the density of water at 4 degrees centigrade is equal to 1 kg per meter cube. So, this becomes, this is equal to 1 kg per meter cube. So, the specific gravity of a substance is just the density of the substance multiplied by 10 to the power minus 3 in a kg per meter cube. However, it is numerically equal to the density in the CGS units. Okay. So, this is equal to 10 to the power minus 3 into density of the substance, and I should write numerical value because this is dimensionless in and this is equal to, simply equal to so if this quantity is quoted in CGS units, then we will not have this 10 to the power minus 3. So, this is how specific gravity is defined. So, let us talk about an important concept in the context of fluids, that is liquids and gases, that is the concept of pressure. As we know that pressure is defined as the force exerted per unit area. So, let us write it with a symbol P is equal to F by A, where F is the force or the load that is given to a certain object, and A is the area over which the force acts. And the SI unit of pressure is Newton per meter square, or it also has a name as Pascal, and 1 Pascal is equal to 1 Newton per meter square. So, let us just consider that a person whose weight is 60 kgs and his weight, say, is equally distributed by his 2 legs, and each foot has an area of say 600 centimeters square. So, the pressure that he would be giving on the ground, so his weight is equal to 60 into G. Just for now, let us take G to be 10 meter per second square. So, this is equal to 600 Newton is the force that is exerting, and so this is equal to F, and so the pressure is F divided by his 2 feet, which has, say, an area of 600 centimeter square. So, this is equal to 600 Newton divided by 2 into 600 into 10 to the power minus 4. So, each feet has an area of 600 centimeter square. So, there are 2 feet, each foot has a area of 600 centimeter square, 2 feet will have 1200 centimeter square. So, this is equal to meter square. So, 600 will cancel and this will be 0.5 into 10 to the power minus 4 Newton per meter square. So, that is the pressure that he exerts due to his own weight. So, now let us look at an important point about pressure exerted by fluids. So, fluids exert pressure on a body from all sides, and so let us particularly talk about pressure due to static fluids. So, we have a container, it is filled up to water till that level, and there is a cube and this fluid exerts a force from all sides, and this force acts normally on the surface of the material or the cube. And what I mean by normally is that the forces act perpendicularly as it is shown here. Had there been a non-perpendicular component, that is a component which is not normal to the surfaces, then there will be a component of the force which is parallel to the surface, such as say this surface. And if there is a component that is parallel to this surface, by Newton's third law, this cube will in turn exert a force on the fluid equal and opposite to that. And because of that, the fluid will be set in motion, which is contrary to what we have assumed, that the fluid is static. So, there can't be any component of force which is acting at a given angle to the surface. It has to be always normal to the surface of the material. So, this is the basic notion of pressure due to fluids. Let us now compute that how to calculate the pressure due to a fluid for a given body. So, let us take again an open container as we have taken earlier. Let us take a level of water and let us take a say, just to be keeping our discussion simple, let us take a cube and let this height be h. And so, we are this cube is of height h, the density of the liquid equals to rho. So, the liquid exerts a pressure on the bottom surface of this cube, which is of magnitude. So, F is equal to mg and this is equal to h, m is equal to v rho and a g, and we are talking about a column of water of volume V. So, according to this question, V is equal to the height times the area of cross section of these bottom section. So, this is of area A, and so this is equal to H A rho G. Since pressure is defined as force by area, so the pressure is equal to F over A, which is equal to H rho G. So, the pressure due to a fluid at a height h below the level of the fluid is H rho G. So, which means that greater the height of the object, the pressure will be more. So, P simply scales as H, given that rho and G remain constant. But there is a small problem there. We are taking rho to be constant, which means the density of the liquid remains constant, which is pretty correct, by and large correct in the context of liquids, except for the case of ocean water, where there is an enormous mass of water. If you consider it a point at a depth h, which is significantly below the sea level, then there could be a change in the density of the water with height, but without getting into that problem, we can say that even for gases which are largely compressible, there could be significant variation of density with the height or with the distance from where it is being measured. So, we actually need more direct calculation of pressure, how it varies as a function of depth in a fluid, not necessarily in a liquid, but in a fluid. As soon as we talk about a liquid, we can safely assume that the rho is constant. However, we need to know this relation. So, for doing that, let us take this case. We will draw this same drawing as we have done, excepting that. So, this is the open container, it is filled up to, the water is filled, or a liquid is filled up to this level, and let us take a small disc like water or the liquid that we are considering, and which is measured from the bottom, which exists at a distance y from the bottom, and the slab is of thickness dy. Okay. So, we are going to calculate the pressure due to static fluid. For that, we are taking a fluid or a liquid in an open container, and we are measuring the distances from the bottom of the container. We have taken a certain mass of water, which is at a distance y from the bottom, has a thickness dy, and the liquid has density rho, and we need to calculate the pressure. So, what are the forces acting on this? There is a force that is acting upward, or let us call it the pressure and multiplied by the area of cross section of this slab, which is the force acting which is due to the fluid and in the upward direction. There is also a force acting down, which is say a P plus a dP multiplied by A. So, we have taken pressure at a height, or this is rather a distance y as P and pressure at a height, again which what I mean is distance, is equal to P plus dP. So, this is at height y plus dy, again measured from the ground, is P plus dP. So, the force due to the fluid acting upward is P A on this bottom surface of this disc. The force that is acting downward is P plus dP into A. A denotes the area of the slab, and of course, we also should consider the effect of gravity. So, the gravity this there will be so just between before we write the gravity. So, there is a P A so this will be P plus dP A minus P A. So, this is downward and this is upward. So, this is the fluid pressure. Also due to the weight of, so let us write it as due to gravity. Let us write that as dF and G, which is equal to dm into G. So, this G subscript stands for gravity and this G stands for acceleration due to gravity. So, dm is the mass of this disc of the liquid, and this is equal to rho G and dV, which is equal to rho G A dy. So, again this is acting downward. So, the net force is equal to P plus dP A minus P A and a plus or we can write it net force upwards will be P A minus P plus dP A minus rho G A dy. Now, at equilibrium this net force is going to vanish. So, then we can write that P A minus P plus dP A minus rho G A dy equal to 0. So, if we cancel A from both the sides, that is divide both sides by A, I get a simple differential equation of the form dP dy equal to minus G. So, this solution of this differential equation will give me the variation of pressure as a function of y. There is a negative sign which tells you that the pressure will be more if the height, that is this distance from the bottom, is less, which means that if you talk about the height from the top surface, then pressure will actually become more as the height or the depth into the water as it increases, the pressure will be more. Since the distance is measured from the bottom surface, we are getting a minus sign, which is which makes sense, because we need to have as the water column gets bigger and bigger, it is going to exert more force at a given point. So, this is my defining equation, which should give me the variation of pressure as a function of the distance, either measured from the bottom of the container, or in other words, it can be measured at the top of the container. So, what we are trying to get at is the following, that we have considered here the fluid pressure and pressure due to or rather this is the force due to the fluid pressure, and this is the force due to gravity, but there could be an additional pressure that could be acting, which is usually the atmospheric pressure. Let us see that how we actually get this atmospheric pressure. So, I hope this part of the discussion is clear. So, now we go ahead and calculate P as a function of y by solving this differential equation, which means that we are going to integrate this equation in order to get P as a function of y. So, that is obtained. So, a dP integrated from a P1 to P2, these values of P1 and P2 are really arbitrary, which can be fixed according to the given problem. And now, I am going to write this as minus rho g dy and integrated from y1 to y2. So, there are 2 points y1 and y2, which are say arbitrary. Y1 is the distance of this point, say point A, from the bottom of the container. Y2 is the distance of the point B from the bottom of the container, where respectively the pressures are P1 here at A and P2 here at B. So, we have to solve this equation. This is fairly easy to solve. We simply integrate it and we continue writing with a minus sign, and so P2 minus P1 equal to minus rho g y2 minus y1. You must have noticed that here we have taken rho and g to be constants, and that is why they are taken out of the integral. However, as we told that either for gases or for liquids in a huge water mass such as an ocean, you may not have rho to be constant. Rho could be a function of y, and that functional dependence needs to be known in order to put it into this equation and integrate. Suppose rho is a linear function of y. Suppose in some problem rho is equal to alpha y, in which case we should not put rho to be a constant and take it out of the integral. Rather, this alpha, which is assumed to be a constant here, which can be taken out of the integral, and this will be an integration of y dy, in which case it will not be y2 minus y1, but it will be y2 square minus y1 square divided by 2. In any case, we are not specifying the functional dependence of rho, and it is taken to be a constant here, and we can write this equation. So, this is how the pressure difference between 2 points which varies with the distance measured of the 2 points from the bottom of the containers to be like this. Now, let us assume that that my y2 is this entire height of the water column measured from the bottom, in which case my P2 becomes simply equal to P 0, which is the atmospheric pressure. So, this is the pressure due to the atmosphere, which is known as the atmospheric pressure. So, that is equal to P 2, and my Y 2 for this particular case, my Y 2 is equal to call it 0, or rather let us call it as H, and we can get or if you call this as the total height of the water column, and now we can measure it from here and absorb the negative sign, in which case we can write this instead of H, we can write this as 0. That is, we are now no longer measuring the distance from the bottom surface, but we are measuring it from the top surface, in which case my Y 2 becomes equal to 0, and my Y 1 let us say becomes equal to H, and then my P 1 becomes equal to P that I want to calculate, and Y 1 becomes equal to H. So, under these two conditions I can put it, in which case what I want to do is that I want to absorb this negative sign and call Y 2 to be equal to 0, because now no longer I am measuring it from the bottom surface, I am measuring it from the top surface, and now my P 2 minus P 1, which becomes equal to my P 0 minus P, and my the right hand side, which is minus rho g Y 2 minus Y 1, now becomes equal to rho g H, and my pressure becomes equal to P 0 plus rho g H. So, this is the final result that we wanted to obtain, which says that the pressure at any given point, which is at a depth h measured from the top surface of the liquid, the pressure at a height h, at a depth h inside the liquid is equal to the atmospheric pressure plus the rho times g times h. And so, that is the expression for pressure that we wanted to calculate. So, this part is due to the atmospheric pressure, and this part is due to the fluid. Having looked at the expression for pressure, which is given as P equal to P 0 plus rho g H, this being the atmospheric pressure as we have discussed, and this is the pressure due to the liquid column of height h. We now want to do some problems using this formula, that is pressure due to liquids, which is given by this. So, let us do a problem which says that the surface of water in a storage tank is 20 meter above the water tap in the kitchen of a house. So, this is understandable that there is a storage overhead storage water storage tank which is there on the terrace, and the distance where the kitchen is or the kitchen tap is, the storage tank is located 20 meters above the kitchen tap. So, the question is calculate the pressure at the tap, and of course, given that density of water equal to 1 into 10 cube kg per meter cube. This density is denoted by a quantity called as rho, which almost looks like P, but please do not distinguish this from P. It is called rho RHO. So, this is equal to rho of water. So, now the pressure at the surface of the tank, that is at the surface of water inside the tank. So, there is atmospheric pressure, and the same atmospheric pressure also is there at when the water is issuing out from the tap. So, essentially the pressure difference is simply given by so delta P is the pressure difference, which is simply given by rho g into H, where rho is of that of water. So, this is equal to 1 into 10 cube kg per meter cube, g is 9.8 meter per second square, and H here is 20 meters. So, if you do this, it becomes 1.96 into 10 to the power 5 Newton per meter square, which is also called as 1.96 into 10 to the power 5 pascals. So, this is the pressure difference that is there at the between the surface of the water level inside the tank to the tap, the nozzle of the tap from which water issues out. So, this is a simple plug-in type of example. Let us do another one. Again a plug-in type, however, it is related to human body again. So, what is the difference in blood pressure between the top of the head and the bottom of the feet of a 1.60 meter tall person standing vertically. So there is a person who is 1.60 meters tall, and you are needed to find the pressure, the blood pressure, the difference in the blood pressure between the top of his head from the bottom of his feet. And the person is assumably standing vertically. Now, the input that needs to be given in this case is the density of blood and just keep in mind that this density of blood that I am going to give you is actually the average density of blood, because the blood consists of the blood plasma, which has a little less density as compared to the other cells that make up for the blood, which has a little more density. So, this is the average density of blood, which is 1060 kg per meter cube. Just take a note that this value for water is 1000 kg per meter cube. So, blood is a little more dense than water. So, again the pressure difference is given by delta P, it is equal to rho G H. Rho for blood is given as 1060 kg per meter cube, with a G to be 9.8 meter per second square multiplied by 1.60 meter, and this comes out as 16620.8 Newton per meter square. Okay, so this is the blood pressure difference between the top of his head to the bottom of his feet. So, let us do another problem. And the problem concerns, which all of you might have felt at times, that you have either traveled up through a hill and or traveled down very quickly, descended from a hill very quickly, or it might have happened when you have traveled in an airplane. Inside the airplane, the pressure is pretty much taken care of, but still one feels uncomfortable at times because there is a pressure build up in the ears. And what happens is that there is a pop in the ear, which means that some air is released to equalize the pressure between the inner part of the eardrum to the outer part of the eardrum. And this, as I told you, that this can also happen if you are climbing a hill or you are getting down from a hill very quickly, and this can cause this popping of the air, as it says. So, if it does not pop, then there is a pressure that builds up, or rather there is a force that is developed, and that is why the ear starts aching. So, the question is, what is the, so when you, not what is, when you run up a tall hill or run down the hill quickly, the ears pop. and as I told, pop means that some air is released from the ears, and this is due to the buildup of the pressure, due to that that the body takes a little while to get accustomed to, suppose you are climbing down a hill very quickly or you are running down a hill very quickly. So, the pressure difference that you initially had and after you have gotten down quite a few say 1000 feet quickly. So, then this pressure buildup can happen. The question is, suppose this did not happen, what would be the force on the eardrum of area 0.5 centimeter square if change in altitude, which means height, altitude, or you can just simply write it as height, of 1000 meter takes place. So, if there is a height difference of 1000 meter that takes place, and if the ears do not pop, so what is the pressure developed, and because of that pressure developed, what is the force that is exerted on the eardrum. So, again P equal to the pressure is equal to H, rho and G. Now, it has to be given that the rho of air, that is the density of air, it's 1.29 kg per meter cube. So, 1000 meter multiplied by 1.29 kg per meter cube multiplied by 9.8 meters per second square, and this thing when you calculate it, it comes out to be 12642 Newton per meter square. So, this is the pressure that is developed between the inner part and the outer part of the eardrum. Because of this pressure, there is going to be a force which is equal to the pressure multiplied by the area, which is 12642 Newton per meter square, and you multiply it by 0.5 into 10 to the power minus 4 meters square. So, the meter square will cancel and this becomes equal to 6.32 Newton. So, this 6.32 Newton is a force that is exerted on the ear. Now, you can take this as suppose, just for the argument's sake or making matters simple, let us take G equal to 10 for now, and which means that there is a weight of 0.6 kg that is exerted on the ears, and this is most of the times this is not an unbearable situation, but however, you would find actually children crying inside the airplane, and the reason more often than not is going to be because of this pressure that develops, and that creates an ache and the child cries. So, we have looked at mainly so far The density of liquids, we have defined density, and we have also looked at density of solids, liquids and gases, and we saw that the density of gases is at least something like 3 orders of magnitude less than that of the other solids and liquids. And we have also learned about specific gravity, and also we looked at the pressure that is exerted by a liquid column of height h, or the pressure that is felt at a point inside the liquid at a depth h from the surface, and used that result to compute some simple problems so far.